All right, team, let's finish up chapter 19. Hopefully you're keeping up with all this material. I hope I'm articulating the material well for this class. Stay calm, keep on studying. Hopefully you learn just as much through online learning as we do in lecture. Okay, so this is our last segment of chapter 19. We're going to finish up the carbohydrate section of this module. So to finish off our learning objectives, like I said, we're covering carbohydrates. I do want to tell you that we have begun learning some reactions. For this chapter, I sent you a reaction guide, so please be sure to take a look at all the chapter 19, 20, and 21 reactions, as that might aid in you studying for this upcoming exam. Chapter theme, Hebrews 3, verse 4. Every house is built by someone, but God is the builder of everything. Carbohydrates are an incredibly important class, and I hope that you're seeing that as we study these large class of biomolecules. Okay, here we go. Last class we talked about what carbohydrates are, how to kind of look at them, and how they're the hydrate of a carbon, though they don't actually bear a true water molecule on them. It's just their molecular formula and how it's put together. We talked also about the Fisher projection, the L, aldo, hexose, or those kind of distinctions, and then we talked about how it can cyclize to form either a 5-membered ring, which we called a furanose, or a 6-membered ring, which we called a pyranose. I mentioned to you that there was something called the anomeric carbon, and it formed based on the approach of the hydroxyl group at either C4 or C5 to the aldehyde or ketone. And if it approached one way, it might cause the quote anomeric carbon, which is nothing more than the hemiacetal carbon, to have the hydroxyl group pointing up or pointing down. Okay, so now we're going to really unpack what this means. So in cyclic molecules, we need to identify it as an alpha or a beta. Okay, alpha or beta, judged by the position of the newly formed stereocenter at C1 and C4 or C5, meaning this carbon that I'm hinting at in red. Okay, that's what judges whether it's alpha or beta. And then you're also going to look at the carbon just to the left of the oxygen in the ring. So that's C1. You're also going to look at that carbon in furanoses, or this carbon that I'm outlining with the red dot in pyranoses. Okay? And so if you're looking at a furanose, you're going to compare C1 and C4. If you're looking at a pyranose, you're going to compare C1 and C5. This is the carbon at C1. It's going to be called the anomeric carbon. If the new stereocenter's OH is cis to C4 or C5 group, it is called beta. Okay, it's going to be called beta. If it's trans, it will be called alpha. Okay, what does this mean? Let's take this particular anomer right here shown in this slide. You may notice that in this one that I starred, on C1, this OH is pointing up. Hopefully you would agree. And now what I'm going to do is I'm going to focus my attention over to C4. It has an H on it, but it also has a carbon-based group. The question is that carbon-based group up or down? It's also up. So because they're both pointing up, we're going to call this cis, okay, aka beta. When looking at the alpha anomer, you may notice that at C2 now the hydroxyl group is pointing downward, but at C4 the carbon group is pointing up. Since they're trans, we're going to call this alpha. Take a look at the 6-membered rings. Do the same thing, but this time compare C1 to C5. Notice that the hydroxyl group on your anomeric carbon is pointing up, and so is your carbon-based group on carbon 5. Since they're both cis on the same side, cis is same, it's going to be called beta, whereas down here your OH is down, your carbon-based group is up. We're going to call that alpha. Okay, these are called anomers. C1 is called the anomeric carbon. And these structures are called anomers of each other whenever you have an alpha and a beta. Of note, I want to introduce to you a new term, mutarotation. It's the effect that a beta anomer, such as this one I'm starring, if it were to go back to the open chain model and reform as the alpha and interconvert back and forth, that's called mutarotation. It's the interconversion of alpha and beta anomers. And you may also see this little box down here. Anomers are examples of what's called epimers. Epimers are diastereomers that only differ by one stereocenter. So it's just a definition of a diastereomer. So enantiomers are non-superimposable mirror images. Diastereomers are not enantiomers, but they are stereoisomers having one or more stereocenters change. But just make sure you didn't completely flip the whole molecule to form an enantiomer. An epimer is a version of a diastereomer in which only one of these stereocenters is changed, okay? And so you may notice, say, these pyranoses right here. Every other stereocenter is the exact same. The only one that flipped is at C1. And so you would call this an epimer. These are epimers of each other, or the whole mutarotation is called epimerization. This is going to be probably the toughest, the toughest slide. I, in this class, make you convert from a Fisher projection to a Haworth and vice versa. Now, one thing I did not make clear in the last slide was use of mnemonic devices. So remember, beta equals cis and alpha equals trans. The way I remember this is in the alphabet, A, B, C. So remember, B is next to C. Beta is cis. So that's how I remember. B is next to C in the alphabet, so beta is cis. Alpha is going to be the opposite, so trans. Now we're going to be converting Fisher projections to Haworth projections. And this is not easy. It's not obvious unless you have a good grip as to what you're looking at. So let's take a look right here at glucose. You have this aldehyde right here, which is going to be your anomeric carbon. Okay, so that is going to be your alpha or beta, depending on what I tell you it's going to be. The meat of this molecule, 2 through 4, those are fixed. Those stereocenters are not changing. So you're going to have to pay special attention to the direction they're facing. And then lastly, carbon 5 bears the hydroxyl group that is doing the attacking, meaning right here where it says right and it's pointing to D, that is the O that finds itself in the ring, okay? It's that same O right there, okay? So let's look at how to do this. Now let's say in this arrow I said make the alpha anomer. I say make the alpha anomer. What you're going to do is you are going to take and you're going to draw a 6-membered ring. Why 6-membered? Because I'm using carbon 5 to do my attacking, not carbon 4. Okay, I might say make an alpha pyranose. And that's exactly what you're going to do. So you draw the pyranose and you notice it needs to be alpha. But you may notice right here, based on what we learned in the previous class, that that last chiral carbon, when the OH is on the right, it's going to be D. Okay, it's going to be D. I'm going to go ahead and tell you that the D isomer looks like that. Okay, CH2OH. You're going to have an H below the ring. Just trust me for now. And then I told you that it's going to be alpha. Therefore, we're going to put the OH group down because when you look at this, and I'm going to change colors to emphasize my point right here, that group and that group are opposite of each other, therefore it's alpha. Okay, hopefully you're tracking with me. Moving on, we don't know what goes right here, or right here, and we got to figure it out, okay? Well, the way I first learned how to do this was I said Labrador. And the way I solved it, and this only pertains to carbons 2 through 4, okay? Just make that clear. It only pertains to these carbons right here. Labrador. Left, above, below is right. Whoops. So it seems I hit a button and I deleted all my clippings, but I really didn't want to have to re-record this entire slide. So I just wanted to continue with what I was saying already. So remember Labrador. Left above, below is right, only for carbons 2 through 4, meaning right here. And so what you may notice is I already told you that that was going to be an alpha designation. And you know that it's alpha because it's on carbon 1, it's down, and at carbon 5, it's up. I told you to trust me that because this is D, that this is going to be a CH2OH. I'm going to tell you why that is in just a second. But let's focus in at carbons 2 through 4, okay? Now, if you apply Labrador, you may notice that right here at carbon 2, it's on the right-hand side. According to the Labrador, left is above, so below the ring is going to be right. So this is right. And so that OH has to occur below the ring. Do you see that? Also, if you look at carbon 3, that OH is on the left. So according to Labrador, left is going to be above the ring. See that? And then lastly, at carbon 4, the OH is on the right. It's going to be below the ring. So right below. That's what I use to figure this out. It works. It's classic. Another way students have found fruitful exercise in determining this is to take this Fisher projection and turn it 90 degrees. Now, if you were to turn it 90 degrees, notice that carbons 2 through 4 look like this. Sorry. And carbon 4. And do you see how that's exactly how the ring is? OH down, OH up, OH down. So it's the same thing. You might get lost in turning it in your head, so I don't always recommend that, but if you're good at that, it works only for the carbons that are part of the meat of the molecule that are unchanging, okay? You can't do it for the attacking hydroxyl group's carbon, and you can't do it for the anomeric carbon, okay? Hopefully this is being clear. So the Labrador helps you cyclize it. Now, I told you earlier that I have a way to solve for how this last carbon right here is pointing up when it's D, and the way I remember this is below the ring, okay? What do I mean by that? If it's L in your Fisher projection, that group is going to occur below the ring. If it's right, meaning it's D, it's going to occur above. And so whenever it's below the ring, you know the Fisher projection had the OH on the left-hand side, okay? And so this takes practice. I'm not thinking you would know how to do this right now, okay? But let's say that I don't know, I'll just do a quick practice problem with you. Let's say I took this molecule, CH2OH. So let me change this up a little bit. Let's do H and OH. And let's say messed that one up, didn't I, class? And let's say I wanted a beta pyranose. Okay, well, first what I need to make sure to know is how many carbons is this? 1, 2, 3, 4, 5, 6. Okay, so that's going to be my skeleton of the 6-membered ring. So I already know I'm trying to make a pyranose, so let me go ahead and draw my pyranose ring. It's going to be a 6-membered ring. And I notice right here that OH is on the left. Therefore, that is going to be my chiral carbon that tells me if it's L or D. Since it's on the left, it's going to be L, and remember, below. Therefore, I'm going to put it below the ring. So I'm going to put CH2OH because that is what's attached to that particular carbon, okay? And then it's also attached to an H, and that OH indicated by the red dot right here is going to be the O in the ring, okay, because it did the attacking. And then I said it's beta. Remember, beta is cis, and so that means that my OH has to occur down in order to be beta. I'll emphasize that by showing that they're both down, meaning beta. I know it's beta because B is next to C. There's so many mnemonics. Beta is cis. Okay, and then lastly, to finish off this molecule, we got to find out where the other groups go. And so what we're looking at is this one, and that one. And so in this one, it's left, which means it's going to be above, according to Labrador. The next one is right, which means it's below. And then the final one right here is right also, so it's also going to be below as well. And so I just successfully converted that structure to the beta pyranose Haworth projection. This is the hardest part of the carbohydrate chemistry. It adds all the elements together of what you've already learned, so you may want to practice this before your next exam, because this is difficult. Hopefully you can go in the reverse, okay? Hopefully you can go in the reverse. You can take this particular Haworth projection that I just starred and deconstruct it to the six-membered Fisher projection, making sure to put the OH on the left because it's L, recognizing that this is an aldose. You know it's an aldose because there's an H right here at the anomeric carbon, and I don't have any ketose drawings right now, so hopefully we can see this happen. Let me know if you have any questions on these slides. I'd love to help you out. Bear in mind that all these are interconverting and they're in equilibrium with one another. So they can interconvert to an open chain model and undergo what I just previously described as mutarotation. So you can have a furanose, the alpha anomer, and it's in equilibrium with the open chain, the Fisher projection. And then it's in equilibrium with the pyranose alpha anomer, assuming you have enough carbons. Some molecules only exist as the pentose or the furanose, excuse me. It's also in equilibrium with the beta furanose. And lastly, equilibrium with the beta anomer of the pyranose. And this all happens through mutarotation. First, I need to take a pit stop and talk about how to determine the number of stereoisomers. This is due to sapling. This is very simple. You'll be asked to identify chiral carbons in a Fisher projection and then asked how many possible stereoisomers are formed. Here's a problem that you might see. So it wants you to first identify all chiral carbons, and all you got to do is click the actual atom, the carbon that bears 4 different groups, noticing here that that's not chiral because you have 2 of the same group. And of course you have to be sp3 hybridized, so that excludes this one as well because that's sp2. Here's how you calculate it: 2 to the n, with n being the number of chiral carbons. So this one, n equals 4, 1, 2, 3, 4. So 16 possible isomers for this one, 2 to the 4th. Okay, di and polysaccharides are distinctions that we use whenever you don't have monosaccharides, but you have more than one carbohydrate put together, okay? So disaccharides are simply 2 monosaccharides bonded together at the hydroxyl group of the hemiacetal. This particular bond is called a glycosidic bond. And polysaccharides, meaning multiple saccharides, multiple sugars, have multiple monosaccharides bonded together. The carbon that was previously the hemiacetal, aka your anomeric carbon, it becomes an acetal when forming the glycosidic bond. So what am I talking about? We did have a glucose molecule here, but then it became bound to a fructose molecule. So remember that this O, before it had this bond, was an OH. Well, whenever it forms that bond, you're going to lose that H, and it's going to bond to another molecule. And now you can see that this is an acetal functional group because it's an OR group and an OR group. Okay, so you have an acetal. You may notice this sucrose does not have a hemiacetal anywhere on the molecule. Okay, not here. There's not another O. There's only one O bound. Not here. That's going to be important later. Here's starch, a polysaccharide composed of repeating glucose units. You may notice that this anomeric carbon, it's now an acetal linkage because that no longer is an OH. Okay, so it's repeating. This bond is now called a glycosidic bond. Okay, Of note, because it wasn't clear in the previous slide, by the way, whenever you have a ketose that cyclizes, just want to show you this, that you see it at least once. Okay, let's say that it's cyclized. That would give you a 1, 2, 3, 4, 5, 6-membered ring. This glitch is driving me nuts. Is it driving you nuts? Okay, and so let's go ahead and make the pyranose of this molecule. And let's notice here that it's on the right hand side, so it's going to be D, which occurs above the ring. CH2OH above the ring, the H below. Then we're going to have to fill in what those groups are. And let's just assume that we made the beta anomer. Here's what I want to emphasize to you. At this, whenever you have a ketose, what you're going to form is a CH2OH. And also, you're going to have an H. Sorry, an OH. Excuse me. You're going to have an OH because this carbon, I'm going to outline it in, this oxygen in green, that oxygen becomes an OH. And so that's this oxygen right there. And then notice you also have that CH2OH, that's that. And so what this was an H with aldoses. Okay, I just wanted to point that out to you guys because it can get confusing when dealing with ketoses. Now, is this one alpha or beta? The way I have it drawn is you still look at the OH, not the CH2OH. So the OH is down. This group here, the D version of this carbohydrate is up. So this is the alpha. Okay, just to fill in the rest of the molecule using the Labrador method. Sounds so silly, doesn't it? Right is below OH, H. See if you can do this on your own. I made this one pretty easy, didn't I? And so I just wanted to show you what a ketose cyclization looked like. All what happens is instead of an H being right there where I'm underlining it, turns into a CH2OH. Oxidation and reduction of carbohydrates. This pertains to sapling problems as well. Going from an aldehyde or ketone to an alcohol is a reduction. You're familiar with this terminology because in organic chemistry I define reduction as gaining hydrogens or losing bonds to oxygens. And so if you look at this particular aldehyde and it becomes an alcohol by the gaining of a hydrogen here and a hydrogen here. So you added hydrogens. That's a reduction. Going from an aldehyde to a carboxylic acid is an oxidation. And so notice you just have an H here, but then you added an O bond there, so that's going to be an oxidation. Carbohydrates are susceptible to both oxidation and reductions in nature. You might have heard of uronic acids or alderic acids, or you might have heard of sugar alcohols. Sugar alcohols would be the reduction, and then alderic, uronic, those are oxidation of carbohydrates, uronic acids, alderic acids. Lastly, is our last content slide for the chapter, reducing and non-reducing sugars. A reducing sugar is one that can form an aldehyde through isomerization. So here's the biggest trick to this reducing and non-reducing sugar. All monosaccharides are reducing sugars. Okay. Whenever you have carbohydrates in your body, they can serve as reducing agents or oxidizing agents. And so all we're trying to figure out is which ones are reducing sugars, which ones can reduce other molecules. And this pertains to Benedict's test or Benedict's reagent. So Benedict's reagent tests for this. And if it's positive, deep red color, you have a reducing sugar. So all monosaccharides are reducing sugars. Another way that you can say this is not by that convoluted definition, one that can form an aldehyde through isomerization, but you can also say if it contains a hemiacetal, and this is going to be really useful in determining reducing versus non-reducing sugar. Okay, and so let's look at glucose down here. Notice right there at carbon 1 it has a hemiacetal, so I already know that that is going to be a reducing sugar. Okay, I know this because if you were to convert it back to the Fisher projection, the open chain model, you know that that will be an aldehyde because there's an H right here, right? If it had CH2OH, that would have been a ketose. Remember right here, you're trying to form an aldehyde through isomerization. However, I told you earlier that all monosaccharides are reducing sugar. So even if it was a ketose, it can isomerize to the aldose to make it a reducing sugar. So that's what's going on there. Don't worry too much about that. More or less know that all monosaccharides are reducing sugars. Look at maltose right here. Maltose is a disaccharide. You may look right here and say, well, Dr. Morris, that is not a hemiacetal. That's now an acetal because of that glycosidic linkage. Well, while that may be true, look over here on the right side of the molecule. That is a hemiacetal, okay? And so that makes maltose a reducing sugar. Through isomerization, that can form an aldehyde. But let's look at sucrose right here. Sucrose. Notice right here, you have an acetal linkage. Therefore, that's not a reducing part of the molecule. And notice right here where it bonds, that also is not a hemiacetal. There is not a hemiacetal on the molecule sucrose. So sucrose is our chief example of a non-reducing sugar. Okay, sucrose is a non-reducing sugar. It would not react with Benedict's reagent. Okay, and so what you're doing with reducing sugars is you're examining your molecule and seeing if you find any hemiacetal. If you find a hemiacetal, it is a reducing sugar. If all what you find is acetals, like in the case of sucrose, it's not a reducing sugar. That's the end of chapter 19. I hope it was a fruitful experience for you. Please bear in mind that I'm not used to online teaching and I'm doing my best with what we have. Soon enough, we'll be back in class learning in person. Blessed is the one, that's a typo. Don't you love typos on the ending slide? Blessed is the one who does not walk in step with the wicked or stand in the way that sinners take or sit in the company of mockers, but whose delight, not obligation, but delight is in the law of the Lord, and who meditates on his law day and night. That's Psalm 1 verses 1 through 2. I hope y'all have a blessed weekend.